Newton's third law often is misunderstood because it just isn't done with enough examples. So I'm going to do some examples to help you understand action and reaction. If I have a 10 kilogram mass and I drop it, there's a force of gravity, mg. Where is the third law reaction? Well, every force is caused by an interaction between two things, this box and the earth. So the reaction force is the box attempting to pull the earth upward with 98 newtons. Obviously the earth does not much respond to that, and this thing does just about all the motion. But these are an action and reaction pair. Note I had to draw two force diagrams because an action-reaction pair are never on the same diagram. A lot of people get confused when they see a box just sitting on a table. They're thinking, okay, we've got mg that way and normal force that way, and nothing happens. So sum of forces in the y is may. If I say up is positive, that means the normal force is positive and mg is negative. And it's not accelerating, so we get the normal force equals mg. So the normal force and mg are equal and opposite forces, but that does not make them an action and reaction pair. Remember, the reaction to this mg is the upward pull on the earth. What's the reaction to the normal force? What two objects are involved in the normal force? The box is being held up by the table. So the box is pushing down on the table. There is the reaction. If you had the table and you push down on it with Fn, that's the action and reaction pair that normal force is a part of. So forces come in pairs, but the pairs are always on two separate force diagrams. Some more examples. Let's say I'm dragging a box along the ground. First, what are all the forces acting on the box? Well, gravity, as usual. We usually start with that unless we're in space. Why doesn't it fall down? Because of the normal force. And this force is partly lifting and partly pulling it to the right. Assuming it's strong enough, the thing's moving to the right, and then we get in opposition a force of kinetic friction. All right, there's the force diagram. Those are all the forces acting on this object. The forces by this object on other things are the equal and opposite forces. So we need other force diagrams. For the mg, we have the earth. For the normal force, we have normal force on the ground, or the table, or whatever that is it's sitting on. The tension, that would be me feeling the equal and opposite force if I'm pulling on it. For the kinetic friction is pulling leftward on the box, and that's an interaction between the box and the floor, so that means there will be a forward force of kinetic friction acting on the ground, which you would notice if, say, it was sandy or something, and so you'd be dragging some of the dirt along with. So there we have the action and reaction. That mg goes with that mg, that normal force with that normal force, that kinetic friction with that kinetic friction, that tension with that tension. Newton's third law always involves two force diagrams, the action on one and the reaction on another. When you're drawing a force diagram, you only care about the forces acting on one object, not the forces by that object. Those are elsewhere. One more example. We've got a box hanging by a rope attached to another box. Let's say it's a rough surface. Let's examine all the forces and then find all the action-reaction pairs. So for this hanging mass, we've got mg downward, generally start with that. Why doesn't it just fall? Because of the rope, the tension. Those are the only two forces on that object. Where are the reaction forces? As usual, the reaction to mg, the earth pulling on the box, is the box pulling upward on the earth. What's the reaction to this tension? Well, equal and opposite, it's up here. It's actually on the pulley. So we would need a separate force diagram for the pulley, and then we would have this tension. In fact, why don't I call it tension 1? If the pulley's frictionless, they're the same. but just to be clear about the directionality of things, that tension one and that tension one are equal and opposite action and reaction pair. All right, what about this one? The forces on this one, we have mg downward, we've got normal force upward, we've got tension to the right, and we've got force of kinetic friction to the left, assuming the surface is rough. Where are the third law reactions? Well, to mg, as always, make that m2g, is a force of m2g pulling upward on the Earth. The normal force is due to the table, so we need a force diagram for the table, and that would have the downward normal force matching that. The force of kinetic friction is going to make a rightward drag on the table, force of kinetic friction. Those are equal and opposite. And the tension, the reaction to the tension, this box is being pulled by this rope, that over there, if this is tension 2, then this is tension 2. So those are all the action and reaction pairs. You see, I had to draw several other diagrams. I had to draw the Earth, I had to draw the table, I had to draw the pulley, because forces are interactions between two objects. They act on each other. So you never see action and reaction on the same object. It doesn't happen. So that's Newton's third law. I hope that clears things up.